Pre-algebra lesson 121, forming solids and symmetry. Now, forming solids, this first section of the lesson, this can be pretty difficult for some people. Sometimes it's just hard to wrap your head around. Some people, it just comes to you very naturally. So have no fear if it comes to you naturally. This will be pretty quick. I'll be able to show it to you. If it's a difficult thing for you to grasp your head around, luckily, one of the formulas we've already memorized for surface area will help us figure this out pretty quickly. We have to find the volume of the geometric solid formed by folding the shape along the dashed lines. Dimensions are in inches. Okay, so what's happening here is the dashed lines are folds. Hopefully these are projects you guys did in grade school where you could fold shapes up into boxes, cubes, triangles, etc. But it is folding along these shapes, and I've got an example I'll be able to show you real quick. Okay, well that took me longer than expected, but I did make an example for you guys. So this is what we've got. We've got our real physical example of what's going on here. So like I said, we have to mentally fold this shape on the dotted lines. So I'll physically show you what you have to mentally accomplish in your brain. So if I were to fold this on the dotted lines, what I should do is I should pick one side as being my base, right? So of these four rectangles, I need to pick one as being the bottom of my shape, right? And I'm going to go ahead and pick this one. It's usually best to pick the one that's surrounded on all fours, right? So because I can kind of mentally fold that, and I can picture all four sides of that piece being the walls of my shape, right? So I'm going to go ahead and fold these, right? Okay, and then I fold this one right there. What we notice is when I fold this, I've got almost the box, right? But then this one side is much longer than the others. Okay, that's the one with the second dashed line. So I'm going to go ahead and fold on that second dashed line. If I can line it up. And let's see here. Did I get it? Nope, too shallow. Right there. Right, I fold on the second dashed line, and it completes the box. Right? So what happened here is these four walls all came up, and then this long side, the extra long side, ended up becoming the roof of the box. Okay, so visually, if I were to keep track of all those numbers, I would see this has a length of 4, these have a height of 3, okay, and then this side has a length of 5, and I can use that information to find the volume of the shape. Or what you could also remember is that a rectangular solid only has a length, a width, and a height. So this is where one of those old formulas is going to come back and help us. So if I'm having trouble visually picturing this, well, if I am visually picturing it well, I can kind of turn it on whatever side I want. I can see that it's got a base is going to be like the rectangle or whatever shape I picked, right? So that's going to have a length of 4, a width of 5, right? So the area of that base will be 20 times the height of 3, which is this wall. Well, oops, which is this wall right here. So to find the volume, I would do 4 times 5, which gives me 20. 20 times 3, which would give me 60 inches cubed for the volume. If you're having trouble figuring that out, what you could remember is that length times width times height formula, which means that if we've got a rectangular solid, there's only going to be 3 numbers. One number is going to be the length, the width, and the height. And if I look at this, I've got 5, 4, and 3. Everything else is just combinations of 5s, 4s, and 3s. So I can see, oh, hey, one of these numbers is the length, the width, and the height. So you could just take 5 times 4 times 3, or 3 times 4 times 5. And then we've got it. So that's a quick trick if you're having trouble visualizing this. Because if I go over here and I did 5 times 4 times 3, even if I did 4 times 3 first, that'd be 12. 12 times 5, that's 60 inches cubed. All right, so that's a good trick for the rectangular solids. Triangular solids get a little bit difficult. We really have to visualize this. No, I didn't make a triangular solid. That's so difficult. Okay. So no, I didn't take the time to make a triangular solid. That's pretty tough for me to create, but it's the same concept. We're just going to pick one side as the bottom, right? So if I pick this as the bottom, or since it's a rectangular solid, it'd probably be better if I pick the triangles as the base, right? So if I need to find the volume, the area of the base would be the triangle, and then the height would be this long side right here. Okay. Yeah, we'll go ahead and do that. So for this one, the area of the base of the triangle, we've got 3 times 4 divided by 2. So I go over here and I do 3 times 4 over 2. That can cancel. So that gives me 6 units, 6 inches squared for the area of the base, times the height, which I have to visually represent like this. The height would be 5. So now I've got 6 inches squared times 5 being the height. That's 30 inches squared. Cool. Or sorry, 30 inches cubed. And that would be the volume of the object. All right, now let's talk about symmetry. Symmetry is how do I say this? It's kind of like the mirroring of an object, or symmetrical, meaning that it's even on both sides, or it looks exactly like itself. So, for example, the human body is symmetrical. If you were to draw a line from the top of your skull all the way down to the bottom of your body, you'd be symmetric left and right. But if you were to draw a line at your belly button, left and horizontally, you wouldn't be symmetrical if you folded your body that way, because you'd have your feet where your head is, and that's not symmetric. But if you folded your right side to your left side, like here, I can show you with my hands. If I take my right hand to my left hand, I match them up, right? They are symmetric, right? They fold and they match up. That's what symmetry is. So things can be symmetric about a line like that, or you can also have symmetry about a point, right? So symmetrical about a point would mean that if I were to draw a line through any direction in this point, the shape would be symmetric. We can see this with an equilateral triangle or a perfect square. The very center point right there makes the shape symmetric. I can draw a line through any direction and make it symmetrical. Okay? So that's symmetry about a line. That's symmetry about a point. Now, let's look at some example problems we get with this. So if we're at example 121.3, they want us to find the area of this symmetric figure. Dimensions are in yards. So the key thing here is being able to fill in some missing pieces. So the symmetric figure being all 4 of these triangles, right? Since it is symmetric about this point, what that means is that this line is the same length as this line, right? And then for this one, this line would be the same length as this line. So we use symmetry to fill in the pieces of the missing triangles. And what we end up seeing is that all 4 of these triangles end up having the same lengths of 2, 2, 2, and 2. So the way that we'd find the area of this symmetric figure, let me go ahead and draw it, and then we'll do it. Oops. Okay, here we go. I've drawn the shape. Now, the point that this figure is symmetric about is that center point right there. So since it's symmetric about that point, it means that the opposite, the corresponding or the mirrored sides are the same. So since this line is mirrored to that line, I can say, hey, that line is 2. Same thing with this one. Since these 2 lines are mirrored, that is also 2. And then I can say the same with these triangles. That line mirrors to that line, so that's also a length of 2. That's also a length of 2. That's all I need to solve this, because all I've got are 4 right triangles. The area of the triangle is going to be base times height divided by 2. So this is going to be 2 times 2 divided by 2. So this is going to have an area of 2 units squared. Same thing with this one. It'd be 2 times 2 divided by 2. So that's 2 units squared. This one's going to be 2 units squared. This one will also be 2 units squared. So the area is just going to be 2 plus 2 plus 2 plus 2. So that's 8. So the area is 8 units squared, right? And that's how I find the area of that symmetric figure. You also need to be able to draw lines of symmetry across objects, so you'll have some practice problems like C and D. If you were to draw lines of symmetry, you could see this is symmetrical this way, horizontally and vertically. It would not be symmetrical diagonally. It just doesn't work. It's kind of like a rectangle in that regard. This one, D, wow, this one could probably have a lot of points of symmetry, because it appears to be symmetric about that point. So it almost seems like there might be an infinite number. I'm not sure. You'll have to figure it out for yourself as I cover up the answer. But that's all we have for this lesson. If you guys have any questions, let me know on the school website, and I will see you in class.